All right, so we look at the next section. So in these sections, we're going to look at the application of Laplace transform to circuit analysis. All right, so we're going to look at three different elements, okay, in circuit analysis. So the first elements we're going to look at resistors, and then followed by inductor and capacitors. Okay, so we have a times domain, and then we have a S domains. And how to convert from time domain or how to transform from time domain to S domains, we are using Laplace. So if you have a voltage source Vt, you have a voltage source which is called as big capital Vs. And if you have a current, in time domains, we denote it by it, and in S domains, we denote it as big capital Is. And if you have a resistor, so in time domains, we denoted the resistor as based on Ohm's law. Okay, you have a resistance, and if you have a current flow, you have a voltage drops. So we have a Vt equal to It multiplied with R. So if you apply a Laplace transform, so what you did is you change this time domain's representation into S domain, so it becomes big capital Vs equal to Is, and remember that your R is you can treat as a constant, so it will remain the same values. So you can see that the resistors in time domains works exactly as the resistor in S domains. So now let's look at the inductor. So we have the inductor equal to Vt equal to L multiplied with the difference of currents. So this is how the voltage that being developed inside an inductor looks like. So if we want to transform this into a S domains, so we need to apply Laplace transformations on each of the components. So we can treat L as a constant. So we put L outside, so we only transforms these terms, okay, these current terms. So if we transform Vt, we will get a big capital Vs, and if we transform this first order derivative, okay, so you can look at the Laplace tables, so it will give us these terms. And if you multiply with L's, you will be able to get that terms. So your final terms or your final equations will be given that ones. So you can see that the voltage that being developed, okay, is equal to, you have two components. The first component is this ones, okay, so where the SL is actually refer to the values of the inductor in S domains. And in time domain, the value of the inductor is just L, but in S domains, the value of the inductor is S multiplied by L. So if you have a node A and B, okay, so you can view this as L or this inductor as a resistance. So when you have a current flow inside of this inductor, so based on the Ohm's law, you will be able to generate a voltage. So that's why you have multiply SL multiplied by IS is equal to voltage. And then for the second terms, okay, so this second terms is usually associated with the initial conditions of our voltage or our developed voltage. So the initial conditions will be in terms of negative. So if you're going to put it, this is positive A and negative B. So based on the Ohm's law, based on KVL, if you're going to apply KVLs, So this will be in reverse directions, where you have positive with negative in reverse directions in order to get negative values. So what it means to you, the value of the voltage in here depending on the initial conditions of that current. So if the initial condition is 0, okay, so the value of the voltage will exactly the same with S multiply L multiply IS, which is exactly looks like the Ohm's law. Okay, so if you want to represent in terms of currents, okay, you can also represent in terms of the currents, where the currents is you put it on the left hand side and the others of the components you put in the right hand side. So that one will be equal. If you display in figure, it looks exactly like that. Next, we look at capacitor. So the equations for the capacitor is given in this time domains. So we have a current which is equal to capacitor multiplied with the rate changes of voltage. So if we apply a Laplace transform, so we can treat the capacitor as a constant. So we put capacitor outside. So we just apply Laplace transforms on the currents and also of the voltage, the rate changes of the voltage. So if you do that, okay, so you can find the transformation in Laplace tables. So it gives you that terms, and if you multiply with this constant capacitance value, so you will get that terms. So the final terms will give you that equations. Here you can see that the value of the capacitor C in time domains will become as 1 over SC inside the S domains. All right, so if we treat this as if we apply an Ohm's law and find out what is the current going through here, so we will have IS equals to VS divided by 1 over SC. So if you brings 1 over SC up there, then you end up with these terms. The second terms, all right, the second terms will come from, this is referred to the initial conditions. So the initial conditions will come from that, okay? So we can say that if we have a V0 divided by S, okay, so based on the Ohm's law, so that one will be equal to current, which is IS multiplied our load, which is in this case is our capacitor, which is 1 over SC. Okay, so you can view as the capacitor as a resistance. So this will give you an equation of Ohm's law. So next, if you want to find, okay, so if you want to find IS, so IS here, so what you do is you take the I over SC, you bring it the other side, okay, so it will becomes 1 over SC. And if you simplify, okay, because this one you can bring up, so you simplify, you will get CV0. Okay, so that's part, okay, so this part will give you CV0. And then the negative part is depends on the direction of the current. Okay, so we in our current IS, we have the current move from positive into negative. But in here, okay, so we have positive that, so the currents will be flowing out from the positive terminal. So because of the reverse direction, so we have a negative. And in terms of the voltage, okay, so this is the value of the voltage. So you can put the voltage on the left hand side. So you modify this based on your equations in here. Okay, so when you represent, it will look like this figure. So now we are look at the examples of circuit problems. So consider we have a circuit problems given in figure 1. So we need to find the values of V naught and based on these problems. So the first step that we can do is we apply Laplace transforms on each of these circuit elements. So we have Laplace transforms for the voltage source, which is ut. Okay, so if we apply Laplace transform for that one, you can refer to the table. So this one will give us 1 over s. And for the capacitor, we have 1 over 3 farad. Okay, so if we Laplace transform capacitor, we got 1 over SC, where our C is 1 over 3. So that will give us 3 over S. And if we Laplace transforms of our inductor, which is 1 Henry, so we get SL. Okay, so S and L value is 1 Henry, so we get S. And finally, for the resistors, it remains the same. So if you redraw again the circuits in S domain, so you will have these circuits with the value of a voltage in S domain is 1 over S, and the value of capacitor is 3 over S, inductor is S, and the resistor value is remain the same. So once we have these circuits represent in S domains, so we can apply our analysis. So in this case, we can apply KVLs, all right? So what is KVLs? KVL stated that the total of voltage inside our mesh or loops is equal to 0. So we have two mesh, 1 and 2. Okay, so before we apply the KVLs, you need to have your reference currents. So that would be your currents, let's say we call it as current I1S, okay? So the second reference currents on the mesh 2, we call it as I2S. So these currents are moving clockwise directions. When we apply KVL at mesh 1, okay, so we need to find what is the representations of voltage across all the elements inside mesh 1. So we have, okay, so we have, this is our voltage 1 over S, but because of the reverse in polarity, based on our reference current, so we get negative 1 over S, and then plus we have a voltage drop inside 1 ohms, so current times the resistors, it will give us 1 times I1S. Plus, okay, so another ones we have a voltage drops inside our capacitor, which is 3 over S multiply with I1S. And because of the other currents from mesh 2, okay, so we need to consider that currents. So due to the reverse polarity with our reference currents in mesh 1, so we put minus 3 over S times I2S. So this is our first equations. So next is we apply KVL around mesh 2. Okay, so if you apply KVL around mesh 2, we can start with 3 over s. So we have 3 over s multiplied with I to s minus from the currents in mesh 1. So we have 3 over s I1s plus with the voltage drop inside 5 ohms. So we have 5 multiplied with I2s. And then we have a voltage drop inside of our inductor, which is S. So plus S minus with current I2S. Okay, so this whole thing will be equal to 0. So that would be our second equations. So if you solve equation 1 and 2, okay, before you solve it, you need to make it simplify. So if you look at equation 1, you have s as your denominator, so you need to get rid of that. So equation 1, you multiply by s, you will end up with negative 1 plus I1s plus 3I1s minus 3I to s equal to 0. So that would be your revised first equations. And for the equation 2, you get rid of denominator s down there. So you multiply the whole equations with s. You will get 3I to s minus 3I1s plus 5s I to s plus s square I to s equal to 0. So that one would be your second equations. So if you solve equation 1 and 2, remember you have two unknowns. One is I1 and I2. Okay, so you can solve that using these two equations. So in the end, if you find your I2, okay, if you find your I2 current will be equal to 3 divided by s to the power of 3 plus 8s square plus 18s. So this is your equations of current I2. So you can see that why we find current I2. So since we want to find what is the voltage V naught T here, okay, so basically in S domains that would be equal to big capital V naught S. So the voltage drop inside the inductor is depends on the current I2S. So that's why when we solve equation 1 and 2, we want our current I2S. So that we can use the current to find the voltage drops. So using the Ohm's law, the voltage drop inside the inductor is equal to V naught S is equal to current, which is I to S, multiplied with the inductor values. So in S domain, the inductor values is S. So we got 3 divided by S to the power of 3 plus 8S squared plus 18S multiplied by S. So these ones will be equal to 3 divided by S squared plus 8s plus 18. So once we got the value of V naught, so next we need to transform this value. Remember this value is in terms of X domains. We need to transform back these values into time domains. So that means we need to apply inverse Laplace to get from V naught S in S domains back to Vt, which is in time domains. So we need to apply inverse Laplace transforms for our value v naught s, which is uh, 3, okay, 3 divided by s squared plus at s plus 18. So you need to refer to the Laplace tables. You need to pick which form is the most suitable to to transform these equations in time domains. Okay, so in here I just give you straight the answers, but I want you to figure out how can these forms can be matched by looking at the Laplace tables. Okay, so when we do the inverse Laplace transform, 3 we can treat as a constant. We put it outside, so we just inverse Laplace transforms for 1 over s squared plus at s plus 18. Okay, so that part, okay, this part you can put it in such a forms where it is equal to s plus 4 square. Okay, so if you do that once, you will end up got s square plus at s plus 16. Okay, so since you got 16 here and supposedly you should got 18, so we plus another 2. So you have these forms, all right? So if you look at your Laplace tables, so if you look at your Laplace transforms, okay, so you need to find which form is quite similar. So just now we have 1 over s plus 4 square and we plus 2, isn't it? Okay, so it is quite similar to that part. Okay, but we need to do a bit of modifications. Where in here we have a omega square. Okay, so by rights we should have here we should have omega square. Okay, so our omega is 2, but we should have square. But if we do this, then the total equation here will change. Okay, so we don't want that to happen. So what we do is we need to put a square root. Okay, so we put a square root. So if we square root 2 and then we square again, so we still get 2. But our square root 2 would become as our omega. And if you can see here is supposed to be omega. So in here we're supposed to put as omega or square root 2. Okay, but if we put a square root 2 in here, okay, so it's changed our total equations. So in order to maintain the original equations, what we did is we multiply with the constants of square root 2. Okay, so that would become 1. So based on this idea, if we do transformations, then we will get this equations where we have exponents negative a. So a is 4t since our omega is square root 2 multiplied by t. Okay, but don't forget you have this in front of you. So if you go back to your final equation in here, okay, so let me erase this one first. Okay, so what we have just now is we need to put a square root here. And then we put a square. And in here we need to replace with a square root 2. But in front of it we need to divide by square root 2 so it will cancel with each other. So in the end, your Vt will be equal to 3 over square root 2 multiply with that ones will give you exponents negative 4t sine square root 2 t volt. Okay, so that would be your final solutions. So next we look at example 2. So in these examples you have position A and position B where the switch is moving from A to B. So the first questions that we need to do is we need to find the current, the voltage V1 and V2 as rational functions of S. Okay, so that is your V1s and V2. Okay, so since we are dealing with capacitor, okay, so we know that the capacitor cannot have a sudden changes. So we need to analyze what happens before this switch is being moved from A to position B. So at times t equal to 0, we have the switch is being moved, but at time roughly before 0, we can denote it as a 0 negative. So it means is roughly before 0, we have these conditions. So we have these conditions where we can say this is 0.2 microfarad and that is 0.8 microfarad. So that would be our positive and negative. That would be our positive and negative. Okay, so we can say that inside of these capacitors, okay, so this capacitor will store a charge. So that charge is represented in terms of voltage drop. So we can denote it as V1. And inside 0.8 microfarad, we can denote it as V2. Okay, so to make analysis, okay, so we assume that is our node A and that is our node B and that is our node C. Okay, remember this is capacitor. So when we want to analyze this capacitor, we will use differential equations to model the changes of the voltage. So in that case, if you want to solve the differential equations, you need to apply Laplace transforms. Okay, so this is the initial conditions of our circuit before the switch is being moved. So when the switch is moved, at time t is larger than 0, so this is the times where the switch is moved from A to B, so we have this circuit. So we have these circuits when time is larger than 0. Okay, so at these times, we have this energy is being built up inside this capacitor. So because of that, we have a rate changes of voltage. So we need to apply a Laplace transform for these circuits in order to analyze the circuits. Okay, so if we apply Laplace transform for 0.2 microfarad, so we will get 1 over SC, 1 over S, 0.2 microfarad. So these ones will give us 5 times 10 to the power of 6 divided by S. And if we apply Laplace transforms of 0.8 microfarad, so these ones will give us 1.25 times 10 to the power of 6 divided by S. Okay, so for resistor, it gives the same values. So we draw again the circuit. Okay, so if you draw the circuit, if you go back to your previous slides, okay, so this is capacitor. So if you transform this capacitor with a voltage drop, you will end up with this figure. Okay, so means you have a capacitor in here and you have an initial values of the voltage. So in that case, when we redraw our circuits, we will have to consider that. So it will look like this. So it will look like this in S domains, where your value of capacitor, okay, can be represented with 0.2 microfarads and its initial value. And for the second capacitor, you have 0.8, so it can be represented with 0.8 microfarad with its initial values. Okay, so what is the initial value in here? So remember that you have your A and C with 100 volts. Okay, so if we look that the voltage supply is 100 volts, and we look at the node A and B, if we know that the voltage supply is 100 volts, uh, since we have 0.2 microfarads, okay, so we can say 20% of the voltage that being supplied will be stored inside of our capacitor. So another 80%, okay, so it's like 80 volts will be stored inside each initial conditions. Okay, so that would be for our first V1s. Okay, for that one V1s. All right, so means we have 80 volts will be the initial values provided by this initial voltage, and another 20% will be stored inside this capacitor. And for the second capacitor, we have 0.8 microfarad. So based on percentage wise, we can assume that 80% of 200 volts will be already stored inside of this capacitor. So the remaining 20%, which is 20 volts, will be stored inside of these initial values. Okay, so we can say in here our V1 is 80 volts because this is referred to the initial values plus with the values that stored by this capacitor. And for V2, we have 20 volts because this is the initial values which is provided, and another part of the energy is provided by these capacitors. Okay, so that's what we get in here. Okay, so you can refer the transformation in capacitor where you have a single capacitor in time domain. So if you transforms, you will have a capacitor and its initial values. Okay, so next, this is in term of time domain. Okay, so we need to change this 80 volts into S domains. So if you do that, you apply Laplace transforms. Okay, so if you apply Laplace transforms of 80 volts, you will get 80 divided by S. And if you apply Laplace transforms of 20 volts, you will get 20 divided by S. Okay, so that means this is actually 80 divided by S, and that one should be at 20 divided by S. So this is your complete circuits in S domains. So why do you need to change this in S domains? Because when you want to solve the changes of voltage that being built or being stored inside the capacitor, you need to solve the differential equations. Okay, so since we don't want to use a normal differential equations techniques, so it's easier for us to borrow Laplace transform to solve the problems. So now we can find our currents. Okay, so our currents after the transformations will be I, big capital I, S. Okay, so if you're using your Ohm's law, so you know that your currents must be equal to voltage divided by resistors. So the resistor in here, you can assume or you can treat your capacitor as a load or as a resistance. So this whole equations will become I equals voltage. So your voltage is 80 volts divided by S plus 20 divided by S. So that is your voltage. And your resistor, you have 5K plus you have 0.2 microfarad. Oops, sorry, the value of microfarad in here. Okay, so let me erase that. So that value should be in terms of S. Okay, so we have done transformation of that. So for 0.2, that one become 5 times 10 to the power of 6 divided by S. And this part is 1.25 times 10 to the power of 6 divided by S. Okay, so that's how it should like. Okay, so I forgot to change the value of the capacitor just now. Okay, so if you put the value of the capacitor, it must be in S domain. So we plus with 5 times 10 to the power of 6 divided by S plus 1.25 times 10 to the power of 6 divided by S. Okay, so if you solve this, okay, if you solve this one, you will get 20 times 10 to the power of negative 3 divided by S plus 1250. So next, we're going to find V1 and V2. Okay, so if you see here, V1 is inside the nodes that consists of 0.2 microfarad, and V2 inside the nodes that consists 0.8 microfarad. So if you go back to this S domain figure, okay, so inside our node A to B, okay, so A to B is these nodes. So this whole nodes will represent as V1, and node B and C will represent as V2, okay. So I forgot to write S here. So this should be Vs and this one should be Vs. Okay, so you can see that inside node A and B, where we have our V1s, okay, so we have a capacitor and the initial value of the voltage, which means when we calculate the V1s, okay, we have a voltage drop being developed inside this capacitor. Okay, so based on the Ohm's law, the voltage drop is equal to Is, which is our current here, Is, 20 times 10 to the power of negative 3 divide S plus 1250 multiply with our resistor, which is the capacitor. So the capacitor is equal to 5 times 10 to the power of 6 divided by S. So this is the voltage drop inside of this capacitor. Okay, and then don't forget you have initial values, which is V1. So basically you need to minus the initial values, right? So this one should be written as minus 80 divided by S volt. Okay, I think this voltage is bigger. Okay, so we should write like this. Okay, so V1S is equal to 80 divided by S minus that one. Okay, so you will get 80 divided by S plus 1 to 50. So this is your V1S. So inside of your V2S, again, you have your initial values, okay? So this initial values is 20 divided by S, and you have the voltage that being developed inside of your capacitor 2, which is 1.25 times 10 to the power of 6, okay? So this voltage that being developed in here will be reduced by the initial voltage. So it will be minus by the initial voltage. So it's minus here. So if we treat this as a resistance, okay, so based on the Ohm's law, we have currents multiplied by this capacitor. So that one will give you 20 over S plus 1250. Okay, so this is your IS in terms of S domain. That is your V1S, and this is your V2S. Okay, so they are in terms of S domains. Okay, so in the next questions, you need to apply, okay, you need to apply IS, or you need to transform IS into time domain. So you need to apply Laplace transform. So I give you a straight answer here. Okay, so if you apply a Laplace transforms, so this ones will give you IT is equal to 20 times exponents, okay, 20 exponents to the power of negative 1250 t milliampere. Okay, so that's for the currents. And for V1, if you apply Laplace transforms, inverse Laplace transforms, you get V1t equal to 80 exponents negative 1250 t volts. And finally, for V2, if you apply inverse Laplace transforms, you get V2t equal to 20 exponents negative 1250 t volts. All right.